Welcome to part 5 in the video tutorial series on organic functional group reactions. This is a very important section. It's going to look at the acyl group transfer reactions. Let's get started. To begin, what in the world is an acyl group, right? So an acyl group is when we have an R group bonded to a carbonyl carbon, and then what happens here, this can vary. All right, so that's why we describe them as an acyl group transfer reaction. This group right here is the acyl group. And of course the R can be a short or long hydrocarbon chain. All righty, now the reason why acyl group transfer reactions are so important is because they're going to be the primary pathways of catabolism and anabolism, right? So when we have if we start in the middle with small molecules. Alrighty, so and over here would be food, and then these would be our large biomolecules. Okay, just fits. Alrighty, so what we've learned so far, right, is we take, right, and remember that food is also large biomolecules. Okay, but these biomolecules may not be the ones that we need for our health. So we will use catabolism to break the food down. And so this will be hydrolysis reactions. And then we'll take those small molecules and we will use anabolic reactions, anabolism, right, to build them up, and that will be the acyl derivative formation reactions. So the reactions that we're going to be studying, right, so anabolism is building and catabolism is breaking down. So the reactions that we're covering in this tutorial will study the hydrolysis reaction of the acyl groups and the acyl derivative formation. So these are the fundamental reactions of metabolism. So we'll start with the catabolic process, catabolism. So for catabolism, you want to think about hydrolysis, right? Lysis, right? Split apart. So these acyl group hydrolysis reactions are where we break down our food. And so here, what we're going to learn is many of the biomolecules in our food have this acyl group, but then this is the part that varies. So we're going to be focusing our attention on this carbonyl carbon and then recognizing that we treat the acyl group, right, as its own as its own species, so to speak. So the hydrolysis reaction is going to come in and split this bond right here, right? So this is where the water will come in and rip apart these large molecules, breaking them down into the small molecules, right? So we call this an acyl group transfer reaction because the acyl group stays together. What's going to change, right, is that the water comes in, the OH of the water always goes with the acyl group. And then the remaining hydrogen from the water, it is going to create a bond with whatever's happening here, which I'm symbolizing as the question mark. And the reason why I'm symbolizing that as the question mark, right, is because this varies. So let's focus on this question mark part, or let's get our bearings now, right? So we have three main reactions we want to study: the carboxylic esters, the thioesters, and the amides. So the first thing to do is focus on our carbonyl group because that helps us recognize the acyl group. Okay. And then for water, we're going to think about water as we have been, breaking it into the hydroxyl and the hydrogen. So then this, the question mark, so right, so the question mark, this would represent, right, so we could have the ether group, the sulfide group, or the amine group. That's why I put a question mark, because this pathway works for all three. All right, so what's going to happen, right? So we know the bond that breaks is the bond between the acyl group and the variable group, the question mark group. That's where the water comes in to split. That's where the hydrolysis occurs. So notice there's our carbonyls, and there's our acyl group. That's why we call these acyl transfer reactions, because the acyl group is not affected. So as the water comes in, it splits apart. So the hydroxyl portion of the water always goes with the acyl group. And then the other hydrogen goes with what I've described, right, as here are the question marks. Oops. Right, so the question mark is either the ether group, the sulfide group, or the amine group. Okay, so now that we have an overview of this reaction, let's practice. Okay, so to practice these though, we're focusing on the functional groups, but remember that our goal is to get to physiological pH, right? So, oops, I showed you the answers. Let me give you this one. Yours should look like this. Okay, right? So physiological pH, right, is 7.4. So if we look, right, at, for example, acetic acid at physiological pH, right, what did we learn about carboxylic acids, right? They are going to form the carboxylate, in this case, an acetate ion. All right, so we're going to need to layer. We're going to learn about hydrolysis, but when we're all done, we're going to apply our acid-base chemistry. All right, so let's get started. Apple flavoring is methyl butanoate. All right, so butanoate, that tells us we have a 4-carbon ester. So there's our 4 carbons, and then it's an ester. So we can put in the ester group, and then the substitution here would be the methyl, CH3. Okay, so there we have the chemical structure for methyl butanoate, which smells and tastes like apple. So if you're a fan of like those Jolly Ranchers, then you too enjoy methyl butanoate. Okay, so now let's look at the hydrolysis reaction of this apple flavoring. All right, so we're going to bring in hydrolysis, so we know we need to have water present. And we're going to be gearing up for biochemistry, so we'll just assume we have an enzyme, a catalyst there to help us out. When we look at our ester, we focus on identifying the carbonyl group or the acyl group, right? So there's our acyl group. And so we know that the water is going to come in and split, right, between the acyl group and our variable group, the ether group here, the carboxyl group. Okay, so we write this out. And so we get the OH on our carbonyl group like we've learned. And then the other hydrogen goes with the carboxyl group. And we have our products. Okay. However, if this is happening at pH 7.4, now we need to show the acid-base chemistry. So what we've learned about carboxylic acids is that they will be deprotonated at physiological pH, but the alcohols, however, they remain neutral. Okay, so remembering our acid-base chemistry, let's draw a thanamine at physiological pH. So we have a 2-carbon chain right? And what do we know? Amines are protonated at pH 7.4. So this information will be helpful as we look at the hydrolysis reaction of an amide, right? We find our carbonyl carbon and identify the acyl group. We recognize that the hydrolysis will occur, right here. That's where we're going to break the bond. It can be helpful to think of water this way. So as we draw the product here, the alcohol group will always come in and bond to the acyl group, and then the other hydrogen will bond with the amine. Okay, but if this is occurring at physiological pH, right, at pH 7.4, now we need to apply our acid-base chemistry. So just like in the previous example with the ester, right, the ester hydrolysis, right, our carboxylic acid deprotonates to the carboxylate, and the amine protonates to the ammonium ion. All right, so I think that the reactions are very straightforward, and I encourage you to just go step by step. Focus on doing the hydrolysis reaction you've just learned, and then if the question specifies physiological pH, then take a moment to remember to apply the acid-base chemistry we have learned about carboxylic acids and amines. All right, so that's really the essence of hydrolysis reactions that we will see in the catabolic processes. Now let's look at the acyl derivative formation. And this would be, and I keep giving you sneak previews, but here we go. Here's the blank version, right? So now we think about anabolism. There you are, right? So this is about building. And so here, our acyl group begins as a carboxylic acid. Right? So this is going to be the reverse of the hydrolysis. Right? So here's our acyl group, and there's the carboxylic acid. And so now what we're going to do is those same groups we saw before, right? They could vary. They could be the OR, the SR, or the NR2, right? So they'd have the hydrogen present. So here what's going to happen, writing a little bit, right? So we can see that we're building, right? So the hydrogen and this is going to come together to produce water, and that's the derivative. We're going to derivatize the acyl group by linking it to a new substituent. So our acyl group once again remains intact. That's our stable base. But now instead of being bonded to a hydroxyl group, it could be bonded to either a carboxyl group, a sulfide, or an amide. Alrighty, so let's see how well you're doing. Take a moment to get your bearings, label your acyl groups, and see if you can figure out the missing reactants. So the first thing I like to do is identify the carbonyl of the acyl group. And I know that this part remains the same for each reaction. So to me, that's a good starting point. And now we look, what's the same, what's different? So we're replacing a hydroxyl with a carboxyl. So that would be our flag that we would need an alcohol, right? So the OH here and this H, that's going to produce the water. All right, so each one of these missing reactants is going to have a hydrogen that combines with the hydroxyl to produce water. So we know that much. And then the rest of the answer is right here, right? SR, or let's see, yeah, we'll do RSH or NR2H. Okay, so notice how the parts in blue match, right? And these all represent what I have symbolized as the question mark. So in an acyl derivative formation reaction, we are bringing together two molecules to create a larger molecule, and water is a byproduct. All right? So this is often called, so in biology, they will call this synthetic dehydration. Okay, so we learned a dehydration reaction earlier, but this is important. This is synthetic dehydration. And the reason why it's, oops, I forgot to end there. Synthetic. All right, because we're going from two molecules, right, that are smaller, right, to a larger molecule, right, oops, plus water. Okay, so as chemists, we refer to it as an acyl derivative formation, and when you get to your bio classes, it'll be called synthetic dehydration. Alrighty, so let's practice a synthetic dehydration reaction here, acyl derivative formation. Let's show the reaction to form rum flavoring, ethyl formate. Alright, so if we look at this name, form, we've seen that before. That tells us hydrogen is the R group. And so that tells us that we have, and the formate would tell us it's an ester. So there's the H for the formate. And there's our ester. And then the ethyl group comes off here. Alrighty. So this question is asking, how would we form this? So we focus on the carbonyl so that we can identify our acyl group. We know that the acyl group is like our landmark. So to form this compound, we start with a carboxylic, oh, I'll put that in green. We'll put that as a carboxylic acid. And there's our carbonyl. And so now the question is, what alcohol do we add? So that's right here. That's what I've described as the question mark. So as an alcohol, it would have a hydrogen. And then we would have O, CH2, CH3, right? There's our question mark. So if we bring these two compounds together, they will form water, and we will link together the formate with the ethanol. So our final product would be the rum flavoring right here, O, CH2, CH3. So there is our carbonyl with our acyl group, and of course, at the same time, we're producing water. Okay. Now, for a grand finale, let's look at the hydrolysis of aspartame, the active ingredient or the chemical formula for NutraSweet. So here we are, and for this hydrolysis, we are going to show our products at physiological pH, pH 7.4. So, whoa, now this molecule looks tricky, but if we use our strategy, we'll be just fine. So I encourage you, the first thing you do is identify all the carbonyls. These are all places of potential hydrolysis. And so now let's take it apart. So here's a carboxylic acid, so that's already hydrolyzed. Here we have an amide though, right? So the question is, are we going to hydrolyze to the left or the right, right? So we're always going to hydrolyze between the acyl carbonyl carbon here and the question mark group. right? So we should be looking for oxygen, sulfur, or nitrogen. So the first hydrolysis will occur there. And then we keep scanning. And we see we have an ester. Once again, will hydrolysis occur on the left or the right? We look for the heteroatom, and we know the hydrolysis will occur here. So water will be coming in to rip apart this molecule in these two locations. So now it could be helpful to simply look at the pieces, right? How many products, how many hydrolysis products will we have, right? So everywhere I've drawn a red line, we're going to split the molecule apart. So we can see that we will have 3 hydrolysis products. Okay, so step 1, let's draw them out. Okay, so the only place that there's going to, this is already hydrolyzed, so this will be where we have our change. So the main thing here is doing our best to correctly draw the R group. Now we say, oh, now I know why they just use R's. Okay, so here is our first acyl group hydrolysis location. And what do we know? We know that we're always going to put the OH group with our carbonyl carbon. Now we come to our second product. So we're going to begin at the nitrogen, and it already has 1 hydrogen present. And we'll finish up the carbon chain. So this is very busy, right? So over here, right, if we're doing the hydrolysis of an amide, right, the OH of the water goes with the carbonyl, and the H goes with the heteroatom. So that's what's happening on the left. On the right, right, the carbonyl always gets the OH. And then we have our last product here, the heteroatom, right, so the methoxide, so that would produce the methanol. So now here's our, we had predicted 3 hydrolysis products. Here they are, 1, 2, and 3. So that was, this is the new information that we've learned in this tutorial. And now to finish this up, to get the final answer, we want to take and show the structures at physiological pH. So show structures at pH 7.4. So remember, here we're only focusing on carboxylic acids and amines. So for the carboxylic acids, we show those as carboxylates. And then the amines, right, we protonate those. And then we have another carboxylic acid, right? So we deprotonate, oops, let me slide this up. So we deprotonate all of our carboxylic acids, and we're going to protonate all amines. So we get to our second product, and we see an amine. So we're going to protonate that. And then we're going to follow along for our carbon chain, make sure we get all of that correct. And now we're going to decarboxylate our carboxylic acid. And then for our third product, it's an alcohol, right? So at physiological pH, we are only focusing on the changes of acid-base chemistry of the carboxylic acids and the amines. So there's no change to the alcohol at physiological pH. So here would be the correct answer to show the hydrolysis of aspartame at physiological pH. Alrighty, so that concludes this video tutorial. Please take some time now to work some homework problems, and if you haven't embraced the use of colored pens and pencils, this may be a time to give them a try. I think they'll really help to be able to predict products successfully.